Symbolic Beginnings. Artificial intelligence kicked off in the 1950s and 1960s with optimism. Alan Turing had already thrown out the big question, can machines think? His Turing test proposed that if a machine could hold a conversation indistinguishable from a human, it could be considered intelligent, sparking early excitement about AI's potential. The Dartmouth Conference in 1956 officially put AI on the map, gathering researchers who genuinely believed you could capture human thought through logic and rules. Taking the Dartmouth vision literally, researchers encoded reasoning as explicit rules and facts. Those handcrafted knowledge bases powered early systems to solve math, prove theorems, and run logical inferences. ELIZA, built by Joseph Weizenbaum at MIT, came along in 1966 as an early kind of chatbot that pretended to be a psychotherapist using scripted pattern matching. People loved it, even though it showed just how limited surface-level conversation could be. Then there was Shaky the robot, built at Stanford in the late 1960s. This invention was actually able to move around, combining sensor readings with planning and symbolic reasoning, allowing it to map out its surroundings and understand what to do next. All these experiments were built on the idea that you could encode reasoning itself into symbolic structures, which can be defined as sets of organized symbols that represent real-world objects and processes for information manipulation. But as problems got bigger and the real world turned out to be messier than expected, this approach started showing its weaknesses: early connectionism and the first winter. While symbolic AI grabbed most of the attention, another group went down a completely different road with connectionism. This is a scientific approach to study human mental processes and cognition employing mathematical models known as artificial neural networks. Connectionists believe that intelligence can emerge from many simple, neuron-like units working in parallel and learning by adjusting connection strengths or weights. In 1958, Frank Rosenblatt introduced the perceptron, the first widely known trainable neural network which learned patterns from data instead of following fixed rules. Early perceptrons could recognize simple shapes and letters, sparking real excitement about machine learning. That excitement didn't last, though. Marvin Minsky and Seymour Papert, two leading AI researchers at MIT, published the book Perceptrons in 1969, in which they mathematically proved that single-layer perceptrons had serious limitations. They couldn't even compute basic logical functions like distinguishing when exactly one of two inputs is true. Indeed, the real power of perceptrons, or artificial neural networks, emerged only years later when technology advancements allowed them to be designed with many layers of neurons and weight, enabling the possibility to perform deep training of artificial neural networks, also known as deep learning. Funding agencies lost faith fast and decided neural networks were a waste of time. Money and attention went back to symbolic approaches, while connectionism dwindled to almost nothing. This mess became AI's first winter, when big promises turned into skepticism and people gave up. Neural networks never completely died out, but for almost 20 years they only survived on the sidelines of mainstream AI research, waiting for computers to get good enough to give them another shot. Expert systems boom. AI made a comeback in the 1970s and early 1980s through expert systems. Researchers stopped trying to create general intelligence and instead built rule-based programs that specialized in specific areas. Mycin, which came out of Stanford, could diagnose bacterial infections and recommend antibiotics almost as well as human doctors. XCON was built for Digital Equipment Corporation, one of the greatest American computer companies of that time, to configure computer systems and ended up saving them millions. These systems packed in human expertise using hundreds or thousands of if-then rules, creating tools that actually worked for business and medicine. The whole concept seemed amazing and felt way easier than universal reasoning. Venture capital poured in, corporations invested heavily, and AI looked like it was becoming a real industry. But actually building and maintaining these systems exposed what people called the knowledge engineering bottleneck. Every single rule had to be painfully crafted by experts, and changing something small could create a huge ripple effect of errors. These rigid rules turned out to be incredibly weak when they hit messy, real-world situations. Even though expert systems had early wins, they carried the problems that would eventually bring them down. Second winter. By the late 1980s, all the hype around expert systems came crashing down. Maintaining those massive rule bases got insanely expensive. The employees using those systems found them cumbersome and irritating to work on, and got altogether frustrated with how inflexible they were. Corporations that had dumped tons of money into knowledge engineering started abandoning projects when they realized they weren't getting their investment back anytime soon. Computer hardware couldn't keep up with what AI researchers wanted to do either. The big predictions from the decade before clashed hard with underwhelming results, so governments and funding agencies drastically cut back. This became the second AI winter, turning the tides against the technology even more. Public opinion on AI went sour, and a lot of people figured the field had hit a permanent dead end. Researchers kept working quietly, but progress slowed way down, and the field split into smaller groups. The seeds of something new were already growing, though. People were exploring mathematical approaches that focused less on detailed rules and more on dealing with uncertainty, probability, and incomplete information. Probabilistic and Statistical AI. Instead of hand-coding every fact, researchers embraced uncertainty. Use probability to make the best decision from incomplete or noisy data. At this point, 3 ideas from computer science and statistics were applied to AI and delivered practical gains. The first concept was Bayesian networks, graph models of how variables influence one another that allowed systems to still reason when some pieces are missing. Bayesian networks term was coined in 1985 by Judea Pearl, an Israeli-American computer scientist and philosopher. It then became an established field of study in the late 1980s, after works from Pearl himself and Richard Neapolitan summarized their properties. The second concept was hidden Markov models, introduced in a series of statistical papers by Leonard E. Baum and other authors in the second half of the 1960s. Hidden Markov models were extremely suitable to model sequential processes. Thus, they were a great fit for early speech recognition because they could predict the next sound from the previous ones. The third concept was expectation maximization algorithm, created by statisticians in the 1970s. This algorithm was the simple training loop that gave hidden Markov models and Bayesian networks a practical way to learn from gaps in the data. It allowed those models to estimate missing data, update their parameters, and iterate. This was a major shift. Instead of rigid rules, statistical AI tried to build a full probabilistic model of how the data is produced. For speech, how phonemes produce the audio; for diagnosis, how diseases cause symptoms, and uses that model to pick the best answer despite uncertainty. Statistical AI changed natural language processing, bioinformatics, and computer vision, creating systems that could learn patterns without exhaustive rules. This period didn't produce flashy breakthroughs, but it solved practical problems and made people trust the field again. As the web brought huge labeled data sets and computers got faster, a different strategy worked better. Don't model the entire data production process, just predict the right label. Classic machine learning renaissance. This phase started taking shape by the mid-1990s and was characterized by a focus shift to discriminative models, a class of models used for classification and prediction at scale. Examples include algorithms like support vector machines, boosting, and random forests. These were incredibly good at classifying data and doing predictions with serious precision. Real-world applications of these algorithms are very common nowadays. A spam filter looks at a new email's words, sender, and past behavior and decides spam or not spam. That's classification. A food delivery app telling you 25 minutes uses distance, traffic, and kitchen load to estimate the exact time until your order arrives. That's prediction. The internet's rise provided massive new data sets, and better computing power meant these models could actually be trained effectively. Benchmarks that used to seem impossible started falling. IBM's machine, Deep Blue, beat chess world champion Garry Kasparov in 1997, proving that statistical search could compete with human grandmasters. A few years later, Netflix launched the Netflix Prize, a $1 million public challenge to improve its movie recommendation system by 10% over its in-house system. The winning teams did it by combining learning algorithms, showing that AI could beat human-designed approaches in recommendation systems. Unlike expert systems, these models didn't need handcrafted rules. They learned straight from labeled data and adapted flexibly to new areas. This wave of progress made machine learning the dominant approach in AI, setting up the rise of many apps and websites which used this technology to fuel profits. These methods still relied heavily on feature engineering, though, and had trouble capturing complex patterns without an engineer's help. Deep learning revolution. The breakthrough arrived in the 2010s with deep learning. Deep learning can be considered as the umbrella under which many similar AI models can be grouped. It's the modern approach where large artificial neural networks are trained with lots of data. A neural network can be thought of as networks of neurons and weights. When it has just a few layers, it is shallow. When it has many layers, it is a deep neural network capable of deep learning. GPUs, which were originally made for graphics, became the powerhouses for training deep networks at scale. The main types of neural networks algorithms for which the GPU technology enabled the possibility for extensive training on dataset, and therefore the capability for deep learning, include artificial neural networks, convolutional neural networks, recurrent networks, and sequence-to-sequence models. Artificial neural networks are the basic family. They had been dismissed for decades after the perceptron situation, but came roaring back thanks to more computing power, huge data sets, and new architecture innovations. Instead of engineers handcrafting features, the networks learn those features themselves, from pixels, from audio, from text. Convolutional neural networks are a type of neural network designed for images. They look for small patterns, edges, corners, then combine them into bigger patterns like eyes or wheels. Indeed, these algorithms led the charge in vision. In 2012, a deep model won the ImageNet competition, which aimed to detect and classify objects in millions of unlabeled test images. That same idea now powers everyday things. Your phone unlocking with your face, photo apps finding dogs or beach automatically, and medical tools spotting tumors and scans. For speech and language, networks that can remember what came before, often called recurrent networks, made a big difference. They listened to audio over time while keeping track of previous sounds, so voicemail transcripts and live captions became usable. With text, that memory helps the model keep context in a sentence, improving autocorrect, next word suggestions, and digital assistance. Sequence-to-sequence models completely transformed machine translation using a simple read-then-write setup between deep learning models. One network reads the sentence in one language, another writes it in the other, with a shared internal memory between them. No brittle, handmade phrase tables, just train on many sentence pairs and let the model learn the mapping end to end. That's why app and browser translations suddenly felt much more natural. The highest achievement of this era was the creation of AlphaGo, a state-of-the-art deep learning system which mastered the ancient and difficult game Go, an abstract strategy board game for two players in which the aim is to fence off more territory than the opponent. AlphaGo beat world champion Lee Sedol at the complex game in 2016, with strategies that shocked even the greatest experts. These successes marked a real paradigm shift. AI wasn't narrowly focused anymore and showed capabilities across vision, speech, and strategy. The deep learning revolution didn't solve everything, but it established neural networks as the foundation of modern AI, and the public image was steadily improving. Transformers and foundation models. During the deep learning boom, one specific innovation reshaped the entire field. The transformer, introduced in 2017 by a team of Google researchers in the paper Attention is All You Need. A transformer is a deep learning architecture that replaces recurrence with self-attention. In a recurrence-based model, the state-of-the-art type of deep learning model until 2017, you read a sentence one word at a time and carry a small memory forward. That is slow to train and easy to forget distant words. Attention lets the model look at all the words at once and weight the ones that matter for each position, like scanning a page with a highlighter. So it captures long-range relationships and trains in parallel. One of the fundamental features of transformers is self-supervision, which is the main training process of the model itself. This process consists of hiding a word and asking the model to fill in the blank, or asking it to predict the next word. That lets it learn from raw text without humans labeling everything. Indeed, the process is self-supervised, not human-supervised. Very large transformer models scaled up with self-supervised pre-training on massive, general-purpose data so that they learn broad skills are called foundation models. Examples include BERT, GPT, and T5. Two add-ons made them even more useful. With retrieval, the model can look things up in a database or search index while it answers, pulling in fresh facts instead of relying only on what it memorized during training. With multimodal training, the same architecture can read text and look at images and later audio and video. So it can caption a photo, describe a chart, or answer questions about what's in a picture. Together, these advances set the stage for a new wave powered by a clear recipe: larger data sets, larger models, and stronger performance across nearly every task. Generative Wave. The year 2022 brought generative AI into the mainstream. Large language models like the famous GPT 3.5 and GPT-4 amaze people with their fluency, coherence, and ability to reason across all kinds of tasks. Large language models are the direct outcome of the transformer era. They're just very large transformer networks trained with self-supervision to predict the next word. That means they inherit attention, seeing all the context at once, and the parallel training. Instead of a model that only labels text, you get a model that can produce text, summaries, answers, code, because it has learned the patterns of language at massive scale. Diffusion models like Stable Diffusion and Midjourney made image generation a huge deal, creating beautiful artwork from simple text prompts. Diffusion models do for images what LLMs do for text, but with a different trick. They learn how to turn pure noise into a picture by removing the noise step by step, the reverse of adding grain to a photo. Systems like DALL-E Whisper and GitHub Copilot prove that AI could generate words, pictures, audio, and even code complex applications to the level of a college student. So in relation to the earlier phases, classic ML labeled things, deep learning learned features automatically, transformers made long-range context and scale practical, and from that, LLMs generate language and diffusion models generate images, moving from recognize to create. Creative industries felt real disruption for the first time as AI tools reached millions of people. Companies rushed to turn this into products, with OpenAI, Google, and Anthropic racing to define the market, while open source communities quickly caught up with lightweight models that could run on personal devices. Questions about safety, misinformation, copyright, and governance became front and center. Generative AI shifted things from analysis to creation, from narrow problem solving to open-ended exploration, marking a new phase where machines became collaborators in human creativity. Instead of simply a tool to be used for a task, AI was now becoming like a prosthetic limb for workers and entrepreneurs. The Agentic Turn. The newest frontier involves AI systems that aren't just passive responders, but autonomous actors capable of planning, memory, and solving problems across multiple steps. Instead of generating a single answer, these agents break down tasks, call external tools, and coordinate actions over time. Early examples include AutoGPT and LangChain, which are frameworks that chain large models together into workflows that feel like digital colleagues. Research is exploring how agents can learn to use online tools and services, interact with databases, and even collaborate with each other in multi-agent simulations. Memory modules let them store information across sessions, and planning components help them work toward long-term goals. The vision is an ecosystem of AI collaborators that can operate independently, manage projects, and help humans across everything from research to business in a proactive way, rather than as passive assistants. This potential comes with risks, though. Questions about safety, reliability, and alignment get sharper as systems gain more autonomy. The Agentic Turn might redefine how humans and AI relate to each other, marking the shift from assistants to partners in decision-making and creation.